Hey there, classes. Welcome back. And I believe this is the first video we've done for this particular school year. So here we go. We're jumping on in class today to talk a little bit about gravity, everything from Bohemian Rhapsody and Galileo up to a PHET simulation. I'll show you how to get to those labs. They're fantastic. They're a lot of fun to play around with. And then the tide charts in Pacifica today. So to begin, we're going to turn this off and bring over the brain pop that we went through today. Now, the brain pop was how we started our day, and I'll walk us to the back of the room where we did an actual pendulum simulation. But the very first thing to bring up, and let me straighten the camera, was this formula right here. Now, before students all panicked and said, oh my goodness, we're going to be doing that formula in class this year, not exactly. What I wanted to get across at this level right now is unpacking the formula a little bit. We had a little bit earlier this year already on forces. When we represent forces in science class and physics, we show arrows. The arrows represent both the magnitude, how strong it is, and the direction, the place where the force is acting. And when you look at this, this is basically just saying the force of gravity. My intention here is to kind of demystify, to de-scarify, which is not really a word, to make a formula like this a little less scary. As you get into algebra, this will become more and more of a comfortable thing to look at. This right here, the big capital letter G, it's just a number, it's just a constant. It's a value that we've determined is consistent throughout nature. And when you look at the M1 and the M2, these are just the mass, the weight, if you will, but the mass of two objects. Any two objects, could be the Earth and the Moon, could be, and in this class right now we are sitting in pairs, could be the person sitting in one desk and the person sitting right next to them in another desk. In other words, if we take the two masses and we divide them by the radius, the distance basically between them. Of course, the full distance or radius would be half of that, and you square it. This is called the inverse square law. The big takeaway is this, that when you're looking at gravity, gravity is partly dependent on the mass of the two objects that you're investigating, and it's partly a function of how far apart those objects are. Which gets to the tide charts that we had up a second ago. The tide charts are showing that the moon is the main cause of two high tides and two low tides. That's what the students were asked to get down here. Two high tides and two low tides every day. Now the sun certainly has an influence as well. We'll talk more in detail as we go forward about king tides, about the ebb and the neap tides and so forth. But right now, just keep in mind that the moon is only 250,000 miles away, while the sun is 93 million miles away. Excuse the imperial systems, but those are the ones that the textbook uses. Of course, we use the metric system usually, but the sun is much, much larger. Matter of fact, you take all the planets in our entire solar system, you lump them together, it still does not even come close to equaling the mass of our sun. But the sun is 93 million miles away. Check out this equation again. It's much, much farther away. Now, yesterday we had a couple of notes on Galileo, and of course the famous thing about going to the Leaning Tower of Pisa. Is it Pisa? No, just kidding. Okay, we all know it's the Leaning Tower of Pisa, and as Galileo drops different weighted objects from the Leaning Tower of Pisa, he discovers that, hey, wait a second, Aristotle wasn't exactly right. It looks like the mass of the object, so long as they have the same basic shape, does not affect the time with which it takes to fall. In other words, heavier objects fall at the same rate as lighter objects. This flew in the face of Aristotle. These pictures up here that the students were asked to write down, and I'm going to carry my computer, which I don't usually do, but let's give it a shot. Those pictures right there go along with some pendulums that we have set up here in the back of the room. This first pendulum we have set up has 400 grams of mass and a 53 centimeter string. And we timed it for 10 swings. And we found out it takes just about 1.5 seconds per swing. This pendulum here, 200 gram weight, again 53 centimeters, and we let it swing. We again found that even though it's got half the mass at the end of the string, it does end up swinging for about the same period, about 1.5 seconds. Finally, we did it just to prove the point a little bit further. Controlling for the variables, we have this one with 3 plates, which is 600 grams. We let it swing. And again, a 1.5 second period. Finally, before the students were asked to go to their simulations, we took, again, a 200-gram weight. We hung it from a shorter string and let it swing. We found the period was much, much shorter. In other words, if we control for the variables, the length of the string is what really matters when it comes to determining the period of a pendulum. And that makes sense if you think about what we learned from Galileo. In other words, that the mass of the object does not matter when it comes to how quickly it falls. If you look, and I'm going to reach around my computer here and grab this that we used as a example in class, my metronome here. We know that a metronome is used, of course, when you have time and to keep time when you're doing music. However, if you think about what a metronome really looks like, it's a bit like a grandfather clock inverted. In other words, it's just a weight at the end of a string, and as you let it swing back and forth, if you have the old style grandfather clocks, if you need to make it run a little bit slower, you lengthen the string a little bit, you bring the weight down. If you need it to run a little bit faster, you shorten the string just a little bit. In other words, you bring the weight up. So we put this away. The last thing I ask students to really think about as we continue our investigation of gravity is when you look at the string length, so long as it's consistent and you're controlling for the variables, should not affect the period of our pendulum. The weight should not affect the period of our pendulum as long as the string length remains consistent. Once the string length becomes shorter, the period of the pendulum becomes much, much faster. So looking at the graph that we had down here, this was the homework. The period, this is the length of period, our dependent variable. This is the length of the string, our independent variable. Given a period length and the length of the string, as the string increases in length, our period time should drop. If you look over here, as the mass at the end of the string is changed, given a consistent string length, it should have absolutely no effect on the period. So we're looking at a consistent slope. In other words, when we're looking at these graphs right here, when we actually put these to paper next week, we will talk a little bit about what the slope of this line right here tells us about our experimental variables. So I hope I didn't go too quickly through it, but I wanted to point out that we use pendulums to investigate gravity. That Galileo gave us the idea that objects of different masses fall at the same rates, and we've referred to Newton. Newton gave us that law of universal gravitation, and we'll explore Newton's laws starting next week and pretty much going throughout the year, because one of the things that we do in the 7th grade standards, 8th grade standards, and actually beyond that too, is the engineering design process, and those absolutely depend on an understanding of Newton's laws of motion. With that, don't forget that we have a quiz tomorrow. You may use one piece of paper written on one side, and the quiz focuses on our key terms and gravity, of course, but our key terms from weeks 1, 2, and 3, and our quiz will be on paper in class. And of course, those who are absent, who have excused absences, can take the quiz in the online format, but for everybody else, it is on paper and in class. See you here in class, everyone. Hope you enjoyed today's simulations. Last little thing to throw in, I'll link it down below. Check out the PHET simulations from the University of Colorado, where you can play with the string length, you can play with the masses, you can even change the gravity. You can say, hey, how fast would this pendulum swing here on Earth? How fast would it swing on the moon? How fast would it swing on Jupiter? It's a great simulation. The University of Colorado does some really excellent work with simulations that you can play in your browser. Take care, everybody. See you online. See you here in class. Bye-bye.